Hello friends. So today we are going to discuss the questions which were asked in the year 2000 and 2006 and we have for 2007. And for 2006 we have two questions. So in the first one it is said that a thermocol vessel contains zero point 0.5 kg of distilled water at 30 degrees centigrade, a metal coil of area 5 into 10 to the power minus 3 meter square, number of turns 100, mass 0.05 kg, and resistance 1.6 ohm is lying horizontally at the bottom of the vessel. A uniform time varying magnetic field is set up to pass vertically through the coil at time t is equal to 0. The field is first increased from 0 to zero point 0.8 Tesla at a constant rate between 0 and 0.02 second, and then decrease to 0 at the same rate between 0.2 and 0.4 second. The cycle is repeated 12,000 times. Make the sketches of the current through the coil and the power dissipated in the coil as a function of time for the first two cycles. Clearly indicate the magnitude of the quantities on the axis. Assume that no heat is lost to the vessel or surrounding. Determine the final temperature of the water under thermal equilibrium. Specific heat of metal is 500 joule per kg Kelvin and specific heat of water is 4200 joule per kg Kelvin. Neglect the inductance of the coil. So this was asked in the year 2000. In this case, we are given that there is a time varying magnetic field that passes vertically through the coil, and because of that the EMF will be induced and resulting in the current in the coil, and the coil is having some resistance which is given as 1.6 ohm, and because of that resistance the joule heating will take place and ultimately the temperature of the water and the coil is going to rise. So we start from that only. We say a time varying magnetic field passes vertically through the coil. And because of that, inducing EMF and hence current in the coil, and hence induced current in the coil. Current in the coil. And because of the resistance of coil, it results in the joule heating. The resistance of coil results in joule heating, thus raising the temperature of water as well as the coil, raising the temperature of water and coil. So first of all, we are going to start with the induced EMF, and then we are going to find out all the relative things ultimately, because we are only interested in finding the final temperature as well as the current as well as power, because we have to plot their graphs. So we start with the current through the coil as a function of time. Current through the coil as a function of time. And for that, we start with the induced EMF, which is given as minus n d phi by dt, where n is the number of turns. So let us write this as phi b, and n is our number of turns, which is given as 100, and phi b is a flux through the coil, which is our magnetic field multiplied by area, and area is given to us. Area means area of coil, which is 5 into 10 to the power minus 3 meter square, and B is the magnetic field, and this magnetic field varies linearly with time. Varies linearly with time. So we have two things. It said that first the magnetic field increases from 0 to 0.8 Tesla at the constant rate of at a constant rate between 0 and 0.2 second. Then it decreases at the same rate for the time 0.2 to 0.4. Okay. So you can say that magnetic field changes in the first part. It says that from 0 to 0.2 seconds, magnetic field increases from 0 to 0.8 Tesla. So which basically means that dB by dt, that is a rate of change of you can say magnetic field, is our 0.8 minus 0 divided by 0.2, and which comes as 4 Tesla per second. And in the second case, from 0.2 seconds to 0.4 seconds, magnetic field decreases from 0.8 Tesla to 0. So in this case, we can write that our rate of change of magnetic field is our 0 minus 0.8 divided by 0.2, this comes as minus 4 Tesla per second. Now we can find out the rate of change of magnetic flux. Rate of change of magnetic flux which is our d phi by dt is equal to area multiplied by dV by dt, and area we already know is 5 into 10 to the power minus 3, and rate of change is given as 4, so this comes as 0.02 Weber per seconds. Now we can find out the induced EMF, which is our minus n d phi by dt will be equal to, number of turns are given 100. We just found out the rate of change of flux is our 0.02, and this comes as minus 2 volts. And we have two values, and magnitude in both the cases is same. In the first case it is minus of 4, and in the first case is plus 4. In the second case it is minus 4. So obviously we can just, you can say, remodify this induced EMF according to both the times. So we can write it as during 0 to 0.2 seconds, we have the induced EMF will be our minus of 2 volt, and during 0.2 0.2 to 0.4 seconds, the induced EMF will be coming as positive 2 volts. Now, according to Ohm's law, we can find out the current. So you can say current, which is I, is equal to induced EMF divided by R. Induced EMF is, if we consider only magnitude, we have 2 divided by resistance is 1.6, so this comes as 1.25 amperes. Similarly, we can write it for both the timings. We can say for 0 to 0.2 seconds, we have a current of minus 1.25 amperes, and for 0.2 to 0.4 seconds, we have a current of plus 1.25 amperes, and this process repeats after every 0.4 seconds. See, this process repeats every 0.4 seconds, and it continues up till 12,000 cycles. And this pattern continues for 12,000 cycles. So we found out the current. Now we are going to find out the power dissipation in the coil. Power dissipation in the coil. And its formula is quite simple. If it is represented P, then P is equal to I square multiplied by R. We already know value of current as well as the resistance. So we can say that power will be equal to 1.25 whole square and multiply by 1.6, and this gives us 2.5 watts. And because of the square of the current, even the value of the current is, you can say, the sign changes from positive to negative alternately, but because of this square the power always remain positive. And there is a symmetric variation in the current. So you can say that current reverses symmetrically the power is always positive. Power is always positive. So it means it will be constant for at 2.5 watt throughout each cycle. So we can say, so power is constant at 2.5 watt throughout each cycle. Throughout each cycle. And this pattern repeats, you can say, and the cycle, please remember, is from first, you can say duration is from 0 to 0.2, then it is 0.2 to 0.4. So entire cycle is for 0 to 0.4. So we can say from here that during 0 to 0.4 seconds, our power remains 2.5 watts. And this pattern repeats every cycle for 12,000 cycles. This pattern repeats every cycle for 12,000 cycles. Finally, we need to find out the temperature of water as well as coil. So we can say final temperature of water and coil. Now we have 12,000 cycle, so we can say total energy dissipated over 12,000 cycles. So you can write it as total energy dissipated over 12,000 cycles we can write the formula that total energy E is power multiplied by total time, and we can find out our total time, that will be equal to duration of one complete cycle, that is from 0 to 0.2, and then comes from 0.2 to 0.4. So total cycle is from 0 to 0.4. So we can write this as power, we already know, is our 2.5, and total time comes as total cycles multiplied by 0.4. So we can write that our total energy is equal to 12,000 joules, and this will be converted into the raising of temperature of water as well as coil. So it means this heat energy is shared between water as well as metal coil. This heat energy is shared between water and metal coil. Water and metal coil. So we can say our E will be equal to for water plus energy, heat for the coil. And we can just modify or write the formula for water is our mass of water and its specific heat plus mass of coil and its specific heat. All the things are given to us, and multiply change in temperature. Change in temperature. So we have to find out this delta T change in temperature. So delta T will be our final temperature, which is TF, and initial temperature and their subtraction. So final temperature minus initial temperature. So we substitute the values. We are given as 0.5 multiplied by 4200 plus 0.06 multiplied by 500, and change in temperature is final temperature minus initial, that was given as 30, and this entire thing is equal to 12,000. Now it is quite simple. This will be equal to, we get this as 2100 plus 30, and we have T final minus 30, and it will be coming as 2130 T final minus 30, giving us temperature final minus 30 is equal to 12,000 divided by 2130, which will be coming as 5.63, and this gives us that final temperature is approximately equal to 35.6 degree. And we have to sketch the graphs. So graph is quite easy. For the current, it is going to alternate between negative and positive for each 0.2 cycle, and power will be entirely constant. So let us draw for first of all for the current. So this is our time in second. Here we have our current. This is our, so it is going to alternate something like this. And this will be negative, positive, negative, positive, and so on. So we have this as, sorry, this will be our 0.2. We have here 0.4, 0.6, and here we have 0.8, and the power will be entirely constant for the entire time period. So this is our time in second. Here we have power, and it will be constant at 2.5 watts. So this completes the first question. In the next question, It's a multi, you can say it has 3 sub questions, and it was asked in the year 2006. And it says that a capacitor of capacitance C can be charged with the help of resistance R by a voltage source V by closing a switch S1 while keeping switch S2 open. The capacitor can be connected in series with an inductor L by closing switch S2 and opening S1. This has 3 sub questions. This is your first, and this is second, this is third, and we are given a figure. We have 2 switches S1 and S2, and open and close of the switch is going to respectively change how the entire circuit behaves. And in the first part, it is asked that initially the capacitor was uncharged. Now switch S1 is closed, S2 is open. If the time constant of the circuit is tau, then which of the options is correct? In the second, it says that if the total charge stored in the LC circuit is Q0, then for t greater than or equal to 0, we have to find out the charge on the capacitor basically. And in the third, it says that after the capacitor gets fully charged, S1 is open and S2 is closed, so that the inductor is connected in series with the capacitor. And then we have to find out which of these option is the correct one. So let us start with the first part. And most importantly, it says that the capacitor, when S1 is closed, the capacitor C charges through the resistance R. And in the second case, when S1 is open and S2 is closed, this becomes a, you can say, LC oscillatory circuit. You can say that we can, because of the position of S1 and S2, we can divide the entire circuit into 2 parts. So we can say 2 different circuit configuration. First configuration we can call as RC charging circuit. And this is when S1 is closed and S2 is open. S1 is closed and S2 is open. And second, we can call it a LC oscillatory circuit. In this case, it says that the capacitor is fully charged. Okay, so it's given for LC oscillatory circuit. We have our S1 is opened and S2 is closed. But the important thing which is mentioned here for this LC oscillatory circuit, before the switching, you can say capacitor is fully charged. Capacitor is fully charged. And another thing from this, we can say that the charge and the current in the circuit is going to follow a simple harmonic motion, okay, because of the charging and discharging of the capacitor, as well as the energy storage and between the inductor as well as capacitor. So you can say charge and current in this circuit follow SHM, because there is no resistance between in this particular circuit when S2 is closed, so it is going to behave like a LC oscillatory circuit. And in the first case we can also say that the capacitor charge follows the exponential function. We can say that capacitor charge is exponential. So in the part A, we have to find out that which of this option will be the correct one. Okay. So let us find out what will be the charge after time t is equal to tau in the RC circuit. Charge after time t is equal to 2 tau now, like I said, that the capacitor is going to charge with the exponential equation, so we can write it as in RC circuit when capacitor is charging, the charge at time t will be governed by the exponential equation, and we can say for that our q of t is equal to our q naught 1 minus e, and this comes minus t upon tau. Q naught is a maximum charge, so this q naught is our maximum charge, which will be given as C multiplied by V, and tau is our time constant, given as RC. So at t is equal to 2 tau, we can write this particular equation can be written as q of 2 tau is equal to q naught, and this comes as 1 minus e raised to power minus 2 tau upon tau. Here tau and tau cancels out. We can write this as q naught 1 minus e raised to power minus 2. And I think this was, yeah. So option number B is the correct option. In this case, we can substitute q naught here because it is given in the CV format. So this comes as CV 1 minus e raised to power minus 2. We can solve it a little bit also, and if we can write this, we substitute value of e raised to power minus 2, which is approximately at 0.1353. So we get charge at q tau will be equal to 0.8647 times q naught. So from here we can say that after 2 tau the capacitor has has 86.47% of total charge, maximum charge, not total. 86.47% of maximum charge, and option number B was correct. Option B is correct. Now we come to the second part, and here it is asked that what will be the charge on capacitor in the LC circuit for t greater than equal to 0. For the second part, we have to find out charge on the capacitor in LC circuit for t greater than equal to 0. And it is mentioned that capacitor is fully charged, the switches are closed and open. So because it is given that capacitor is fully charged to Q naught, and at this instant we have our S1 is opened and S2 is closed. So because of this, the circuit is now behaves as a LC oscillatory circuit. So circuit behaves as LC oscillating circuit. So it means charge oscillate between capacitor and inductor. So we can use KVL. KVL gives us that voltage inductor plus voltage in capacitor is equal to 0 because there is no external source, and the voltage across the inductor is our L di upon dt, and voltage across capacitor is our charge oblique capacitance. So we substitute, we can write that our L di upon dt plus Q upon C is equal to 0, and we also know that our current I is our dq upon dt. So we can say that our di upon dt is nothing but a double derivative of the charge. So we substitute it, we get this as L double derivative of charge plus Q upon C is equal to 0, and this gives us that double derivative of charge will be equal to minus 1 upon LC multiplied by Q, and we can find out from here that our Q is equal to minus LC, and we have double derivative of charge with respect to time. Now this is the second order differential equation, and I think one of the options, option number C is the correct one. Option C is correct. And we can further write a little bit of from here. For this particular equation, we can say it is a second order differential equation. Second order differential equation, and which is a, we can say, characteristic of SHM. Characteristic of SHM, and with angular frequency omega will be equal to 1 upon square root of LC, and its solution means the solution of the equation, and solution for Q of t, because it is, you can write this as Q of t is equal to over Q naught cos of omega t. And now we come to our C part. We have to find out the instantaneous current in the LC circuit. Third part, instantaneous current in LC circuit at t greater than 0. We just found out that the current in the LC circuit will be the time derivative of the charge. The current in the LC circuit is time derivative of charge. So we can say our current I of t will be equal to minus dq upon dt. And q, we just found out, wrote that q is equal to this q naught cos omega t. So we substitute it here. We can write that our I of t will be equal to minus t, its derivative, and we can write our cos q naught cos of omega t. If we derivate it, we get this as minus q naught, and we have minus of omega sine omega t, which comes as q naught omega sine omega t. But our omega is 1 upon square root of LC. But omega is 1 upon square root of LC. Therefore, we can say that our current I of t is equal to q naught square root of LC and sine of t upon square root of LC. And we know that q naught is our CV. So we can write that our I of t is equal to CV square root of LC sine of t square root of LC. So we get this as our I of t is equal to V square root of C upon L sine of t square root of L multiplied by C. And we have to find out the maximum instantaneous current. So for the maximum value, the sine of t or sine of omega t will be equal to 1. For maximum I of t, we should be having sine of t upon LC is equal to 1. Therefore, we get that our current maximum is equal to V square root of C upon L. And this was our final part in this question, and the option number D is the correct one. We have option D is correct. We have next question, and it is more or less theoretical one, and it was asked in the year 2006. So it says that modern trains are based on maglev technology, in which trains are magnetic levitated, which runs its EDS maglev system. There are coils on both sides of wheels. Due to motion of train, current induces in the coil of the track which levitate it. This is in accordance with Lenz's law. If the train lower down, then due to Lenz's law, a repulsive force increases, due to which train gets uplifted, and if it goes much higher, then there is net downward force due to gravity. The advantage of maglev train is that there is no friction between the train and the track, thereby reducing power consumption and enabling the train to attain very high speeds. Disadvantage of maglev train is that as it slows down, the electromagnetic forces decreases and it becomes difficult to keep it levitated, and as it moves forward according to Lenz's law, there is an EMF drag force. So based on this, we have 3 questions. First, it asks for the advantage of the system, and second, it asks for the disadvantage of the system, and the third, it asks which force causes the train to elevate up. Okay. So this is quite simple. We can just take the correct one, and in this case, the option number A, in the first case rather, option number A is the correct one, where this there is slight, you can say, this statement, no friction and hence no power consumption. Actually, it should be written that no friction between train and track and reducing energy loss and enabling high speed. So this should be a little bit modification in this part, but anyway, it is the closest one. And for the second, you can say the disadvantage is because of this Lenz's law drag force. Option number D is the correct one. And for the last one, the option number C, because of the magnetic force. So these are the, you can see it is entirely theoretical one. Okay. And we come to the next question. It was asked in the year 2007, and it is based on assertion and reasoning. And it states that the assertion is a vertical iron rod has a coil wire wound over it at the bottom end. An alternating current flow in the coil. There is a conducting ring around the rod as shown in the figure. The ring can float at a certain height above the coil. And the reason given to it, in the above situation, a current is induced in the ring, which interact with the horizontal component of the magnetic field to produce an average force in the upward direction. So this is our, you can say, given as a iron rod, and we have this, you can say, the coil. Current is flowing through the coil, and we have this as a ring, and it says that it levitates or it floats or rises in the upward direction. So first of all, let's try to understand what is the induced EMF, magnetic field, and accordingly we can move forward. So let us first of all find out or write the formula for the magnetic field created by the coil, because an alternating current is flowing through the coil and the direction is not given. So we can say magnetic field created by the coil. Magnetic field created by coil. So in this case, for an alternating current I of t, for alternating current IT, the magnetic field if given as B, which will equal to mu naught n times I of t. Here mu naught is permeability of free space. Mu naught is our permeability of free space, and small n is our number of turns per unit length of the coil. Number of turns per unit length of coil. And the current is alternating, so we can say this our I of t can be written as is our I naught sine omega t. Therefore we can write that our magnetic field is equal to mu naught n I naught, and we have sine omega t, where I naught is a maximum current and omega is the angular frequency. So we can also say that this magnetic field also changes over the time because of the alternating current. You can say this magnetic field changes over time due to alternating current. Now we can find out the induced EMF in the conducting ring. Induced EMF in the conducting ring, and we can write this as our induced EMF will be equal to minus d phi b of dt, where phi b is a magnetic flux, phi b is magnetic flux, which will be equal to our B of T magnetic field multiplied by area. And here area is the cross-sectional area of the ring. A is the cross-sectional area of ring, and we substitute our magnetic field, so we get the induced EMF, we substitute magnetic field, so we get our flux phi of B will be equal to mu naught n I naught sine omega t multiplied by area. Now we can find out induced EMF. So induced EMF is our minus d upon dt, and this is our mu naught n I naught a sine of omega t, and derivating it, we get our induced EMF is minus mu naught n I naught a omega, and we get this as cos of omega t. So it means this is the induced EMF in the conducting ring. This is the induced EMF in the conducting ring. Now this will result in induced current. So you can say induced current I induced will be equal to induced EMF divided by resistance, where R is the resistance of the conducting ring. R is the resistance of conducting ring. Now we substitute value of a formula for this induced EMF. We can write that our I induced will be equal to mu naught n I naught a omega cos of omega t and divided by R. And because of this, you can say induced current, this induced current will generate its own magnetic field. You can say, let us start with the force on ring. Force on conducting ring. So like I said, the induced current creates its own magnetic field. Creates its own magnetic field, and this created magnetic field interacts with the magnetic field produced by the coil. This or we can say which interacts with the magnetic field produced by the coil. Produced by the coil. Therefore, we can say the force on the current carrying conductor in the magnetic field, if we can say the force F will be equal to current induced L multiplied by B, where L is the length of conducting ring. L is the length of conducting ring. And it is said that magnetic field is vertical, so their interaction will be resulting in a vertical component, okay? And the force will act in the opposite direction to the change on magnetic flux. So the important thing is that the force will act in direction to oppose, because of the Lenz's law, to oppose the change in magnetic flux. The change in magnetic flux. So, and which will produce an upward force. Which will produce upward force. So therefore, the expression of the force, we can substitute value of induced current, and this becomes mu naught n I naught a omega cos of omega t divided by r, and this is L multiplied by B. And we can just, you can say, we can also make a further analysis, and we can say that the induced current in the ring will interact with the horizontal component of magnetic field, and both will repel each other. Okay? And the repulsion will be balanced by the weight of the ring, because it will try to lift up, and so you can say the weight will try to pull the ring downward. So induced current of the ring will interact with horizontal component of magnetic field, and both will repel each other, and the repulsion will balance the weight of the ring. And repulsion will balance weight of the ring. We can just represent this by the approximate diagram also. So we have This is our, and we have a ring. Let us suppose it is here in somewhere bottom like this, and we have our ring here, and the magnetic force, the magnetic field lines will be moving in this direction. So at this particular point, the net magnetic field, this is a B, which can be divided into two components. One will be the horizontal component and another one will be our vertical component, and there will be a force acting in upward direction, and we are going to have a weight that is a mg acting in the downward direction. So we can say the option A is correct. Option A is correct. This is the correct one, and I think all the questions are done. Yeah. So these were the few questions which was asked in the year 2000 and 2006 and 2007. This completes all the questions. Thank you.